Greens, a very good afternoon, everyone. My name is Mohammed Inishama bin Mohammed Zawar Razmi, and my FYP project is predictive maintenance from vehicle telemetry, supervised by Ms. Mauma and moderated by Dr. Ng Chiam, which is turning engine telemetry into early and explainable failure warnings. So this is the presentation outline that I'm going to showcase. And modern vehicles continuously stream rich engine telemetry, temperature, pressure, vibration, battery, and more. Yet maintenance is still largely reactive or fixed schedule, so failures are handled after they are happened, or healthy parts are serving unnecessarily. Predictive maintenance can forecast failures before they occur, but commercial tools are proprietary, opaque, and hard to reproduce for study, which is the opportunity this project takes. There's three problems to define. First, maintenance is reactive or scheduled, causing unplanned breakdowns and avoidable costs. Second, sequential telemetry is noisy, high volume, and highly imbalanced, so turning it into reliable prediction is technically hard. Third, existing predictive maintenance tools are closed and unexplainable. The gap is no open end-to-end system, turn vehicle telemetry into early trustworthy explainable failure warnings. The aim is to design, implement, and evaluate an end-to-end explainable predictive maintenance system. There are six objectives. These are the objective and as follows. So, briefly, the lecturer describes the show automatic maintenance shift from fixed schedules to data-driven prediction. And Tesla identified the key machine learning challenges, class imbalance, data quality, and the need for interpretable, trustworthy models. Other than that, classical condition-based maintenance relies on hand-built physical models, while feature-based time series method like T-Fresh make telemetry usable by tabular models. The gap across all of it is almost no open, reproducible, end-to-end explainable application. This is where my contribution is. So now the methodology is as follows. Data generation, feature engineering, exploratory analysis, model and selection, evaluation, and finally deployment dashboard. Where there's always these three principles run through every stage, which is nothing leaks from the future. Data is always split at the vehicle level, and every metric is chosen for imbalanced data. So fleet telemetry is confidential. So a synthetic generator used to simulate 100 vehicles across 60 brands, each with roughly 600 minutes of minute level data. Three physically motivated failure modes, which are engine overheat, low oil pressure, and excessive vibration, develop gradually, and healthy vehicles include hard negative, such as benign anomalies that force the model to tell degradation from noise. Failures are rare, so therefore that's why it's only 2.4% Windows, which shakes the whole evaluation. So the telemetry becomes a 30 rows aligning windows, advanced 10 rows at a time, each summarized into 436 statistical features, such as level, spread, and trend per sensor. Two targets are attached, a binary imminent failure flag and a four-class urgency horizon. The critical safeguard is here. Each vehicle failure time is computed first and every row at all after it is dropped before windowing, so no features can ever contain the failure itself. An automated unit test enforces the guarantee on every run. As you can see here, exploratory analysis confirms four things. The severe class imbalance, so accuracy alone would be meaningless. That secondly, that vibration and temperature statistic separate failure from healthy window most clearly. Also, that features from the same sensor forms correlated blocks, which C and ensembles handles well, and that the urgency classes are uneven, motivating macro average evaluation. The system uses a four-layer architecture, as you can see here. The layer holds telemetry, arcade features, and five-table SQLite database. The model layer holds the deploy XG boost models, calibration, and model registry. The application layer runs the pipeline, and finally, the presentation layer is the 7-page stream dashboard. So there's three models: logistic regression, random forest, and XGBoost were trained on identical vehicle level speed with class weighing. Importantly, I did not pick the deployed model. The pipeline selected it automatically held by the health test PRAC, where XGB boost won, as you can see from the result, against the random forest and for logistic regression, and also the naive baseline. At that threshold, On all stock windows, the deployed model achieved a ROC of 0.99 and a PRAUC of 0.86 with a recall of 0.84 and a precision of 0.59. Concretely, it catches 99 of the 118 imminent failure windows with only 70 false alarms out of 4,762 healthy windows and 1.5% failure positive rate. A single split can flatter a model, so I confirm generalization with fourfold cross-validation group by vehicle. No vehicle appears on both sides of a fold. The honest, conservative result is as it follows. That's roughly 15 times better than naive baseline on the metric that matters for rare events. And I quote this conservative number deliberately rather than only the headline. So the four class urgency, as you can see here, which are as follows. Uh, Most importantly, across the 80 vehicle, 74 are detected before failure, and which is 92.5%. And with median time of 30 minutes, a mean of 31, and about 18% flag more than an hour ahead. The predictive probability should mean what it says. Alert threshold depend on it. Flat scaling align predicted probabilities with observed failure frequencies, cutting the expected calibration area by 75% from 0.0145 to 0.036. So when the dashboard say 30% risk, it really is about the 30%. Every prediction is explained through sharp, globally vibration level, engine duration, and oil pressure dominate the model decision, exactly matching the physics of the three failure modes, which tell me the model learned real degradation, not just shortcuts. Locally, for any flight vehicle, the dashboard shows precisely which signals push its risk up, turning an alert into a defensible maintenance decision. I also audited the model rather than just averaging it. Recall by brand, as you can see here, BM and Honda is the strongest, but drops to 0.52 for Mercedes, a gap of 0.44 that I report transparently with mitigation proposed, such as brand certified threshold or rebellion training. The ablation study removes one sensor group at a time. With vibration, without vibration, F1 collapses from 0.766 to 0. Without temperature, to 0.065. So those two channels carry the signal, which is also practical guidance on where sensing investment matters. Real telemetry is imperfect. I stress tested the model under 10 to 20% sensor noise. PRUC stays around 0.85. With 20% missing readings, it degrades gracefully to 0.798. Losing an entire sensor group hurts more rather than dropping vibration gives 0.73. So in deployment, a science sensor should raise a data quality alert. Everything is delivered through a 7-page dashboard, as you can see here. A live freeze overview, an alert triad workflow, analytics, sharp explainability, notification, account settings, and admin governance, all with role-based access. Rather than describe it, let me show you the real system in a moment. It is engineered like a real software. 23 automated tests across 9 files, all passing through the leakage guard as permanent safety net, password hashing, SQL alchemy with idempotent migration, one configuration file, and a Docker so the whole system reproduces from a clean clone. In conclusion, all six objectives were achieved: the dataset, the leakage safe failures, the compact models with LCGB boost auto-selected, the imbalance aware evaluation, the trust analysis, and the delivered application. The line is the end-to-end explainable system that catches 92.5% of failures at PRAUC of 0.859 with a 30-minute median warning built and tested as a real software. Honestly, stated limitations, the data is synthetic, so real fleet valuation is the essential next step. The brand fairness gap is reported but not yet closed, and operation is batch, not streaming. Future work target exactly those with real OBD2 data, fairness mitigation, and real-time inference. And the practical impact is clear for the operators, insurers, and leasing companies. So thank you very much.